Thank you. That helps clear things up.
Okay, cool. Yeah. All right. Yeah, so we can field homework questions if you like.
Yeah, so I'm looking at from the book, Chapter 2, Problem 6, and it's the traffic flow problem.
Okay.
And Part B is a little, I'm not really sure what it is, what it's asking for. It says, how would you characterize the maximum velocity and the maximum density? And I'm not really sure what characterize means here, but I said that the maximum velocity would probably be the speed limit, and the maximum density would just be like 1 over the length of the shortest vehicle, or the density when cars are in gridlock, bumper to bumper. Was it looking for something else? Do you know?
Let me let me just pull up the.
Yeah, it's page 38 of the PDF.
Yeah, so yeah, so it shouldn't be a very long answer to that question. And so, yeah, and you don't have, okay, there we go. Finally got the book open. Okay. Yeah, so once you have once you know something about whether V is increasing or decreasing, right? That should give you some information, I think, about what the maximum velocity is, right?
Okay, I see. So just the
I mean,
speed the car would
yeah,
move
the
if it
speed
was alone.
itself is that's a function of the density, right?
Yeah. And if it seems clear it's decreasing because they're going to stop if there's gridlock.
Right. So so you're not going to necessarily have a number, right? But yeah, because it's decreasing, then
So something like the maximum velocity would be the speed a vehicle travels if it were alone on the road.
exactly, yeah.
Okay.
Well,
And then
you can represent that mathematically, right? As just
V of 0?
yeah,
Or,
something like that, right?
okay.
Yeah. And then yeah, you should not expect you can have the maximum density end up larger than, well, yeah, for a physically realistic model, you can't have the maximum density go up to infinity, right? So it has to be bounded from above, right? But it's just going to be, some, the supremum basically of your solution, right? So you can give an answer just in terms of your the solution itself, right? The V of U, V of your solution U max is just going to be it's going to be like the minimizer, for instance, of your velocity, right? I think that's what you were saying before.
Yeah. So
I mean,
I guess it was
once
a
you get to
little.
gridlock, you can't accumulate any more cars in that region, right?
Right. So if the cars are bumper to bumper, then whatever the density is, that's the maximum density.
That's the idea.
Okay. So I guess that kind of steps nicely into part C. Because it seems like, so if I assume that at the maximum density, the cars are stopped and the velocity is 0, then part C is easy. I just use like Rolle's theorem. But I don't know if I'm allowed to assume that. And it kind of seems to contradict saying that V is positive. And I think I came up with a counterexample if I don't assume that, where I have V is just a decreasing function of the density. And if it doesn't end at 0, then the maximum will occur, the maximum of the flux will occur at the endpoint instead of in the interval.
Yeah, I mean, well, you can have a decreasing function multiplied by u, and yeah, I mean, you're just gonna differentiate. Is that what you're saying? You're gonna differentiate that, and then you'll get some formula for the derivative of that function.
Well, so
you just want to find a critical point of that, and you want to use calculus to show that it has to be a maximum.
right. So I think that means finding, like using some theorem like mean value theorem or Rolle's theorem to say that the derivative is 0 somewhere.
And you know that v of u needs to be positive at 0, so it's got to be increasing initially at 0, and then
right.
It can only be one critical point, and it needs to be a maximum.
Right, but I think that I was having trouble because if I can say something like V of U max is 0, that when the density is the highest, the velocity stops and goes to 0, then I can do this, and that works all straightforward. But when they say that V is positive, I took that to mean that V cannot be 0. And I came up with a counterexample, so I think I must be misinterpreting the problem, or they've worded it differently than I would have or something.
Yeah, so I guess
Are they
so the idea is that it limits to 0 at U max. So it's only defined on the open interval between like 0 and U max. But then at U max it's 0. So yeah,
I see.
it's badly worded. You're right. Yeah. But yeah, it's going to 0 at U max, where you're getting that shock or traffic jam.
Okay, great. That makes it straightforward then.
Yeah.
And then for D, I still have more things I can try, but they want to find a local maxima, some flux where there are 2 local maxima, and they say hint, make it a quartic. So I was thinking I would just make it some arbitrary quartic, or I guess make V some arbitrary cubic, and then Q is U times that. And then right now I'm just trying to find, I guess, coefficients that work. So I can turn it into like a constrained optimization question. Is there maybe something more direct I can do, or should I just do a parameter sweep for things that work? Or
for D, I think I typically don't make people justify this, but if you just write the idea down for D, like, you're just gonna, you say, you can construct some higher order polynomial that's still decreasing. And so it's doable there. Yeah, that's more of a conceptual question. Yeah, I mean, there are, I think people usually find like sort of the minimal easiest example, I think, which is something like a quartic, but you don't have to go that far. You can just say yes, and here's how you would do that.
Perfect. Thank you.
You're welcome.
I think I had another question. On problem 3, it defines the support to be the set where the function is non-zero. And other definitions I've seen usually say the support is the closure of that set. Um, is that an important distinction, or can I think of it either way for the purposes of using the support in this class?
Yeah, so you're saying there should be closed brackets there. That's where you're asking. Those should be closed rather than open brackets.
Yeah, I don't think it really makes much of a difference for this problem, but in general, is that like a convention I should adopt that will maybe make a difference at some point, or does it not really matter?
Yeah, so I thought the support you always defined as the just the region where the function is not zero. So if you have a function and it hits 0 at 1 and 2, then the support would be the open interval between 1 and 2. So you're saying you've seen
Yeah.
definitions
Well,
where
yes, I
I
think
think
usually
what you're
they
talking
just
about would be the closure of the support in this
well, yeah, well, so I know in the analysis book it defines the support as the closure of that set, and as far as I can tell, the only reason they do it is so they can say things like if such and such has compact support, which necessitates it being closed.
Yeah. Yeah, okay. Yeah, oh yeah, so there's this issue of it being it's like the smallest subset of your domain with the property that F is 0 on the subset's complement. So yeah, maybe that precludes you using open intervals. No, but it should still work though, right? I mean, even if it's an open interval, then the complement of that should be the closed interval where now you include the boundaries in that case. So yeah. So for this class, I'm not going to nitpick about that.
Okay.
You could write this is an open or a closed interval in this case. Yeah.
Okay.
It may be like one of those textbook dependent things. Whether or not you include the limit point or not.
Okay.
But yeah, it may be that the more accepted definition is what you're saying.
Yeah, I didn't get the impression it mattered much because when I came into analysis, I was using this definition that you give. And the only time it sort of threw a problem is when they start talking about, like, if you have a continuous function and you define it this way, the support is never compact because it's an open interval. And they wanted to say things like has compact support and stuff. And so it's just a weird thing I had to get used to, and it didn't seem to matter very much except for in a couple of little nitty gritty detail-y places.
Yeah. I think usually for proofs, this sort of like this closure-based definition is better. So yeah, but I think in this problem, I'm just asking you to draw the regions. So yeah.
Well, I wanted to stick around to see what other people asked, but I don't know if you all are shy or if you're just doing the same thing.
Or if you're hoping somebody else will ask. Yeah, feel free to jump in, anybody.
I kind of have another question, but not about the homework. But if someone else has something about the homework, they can go first. Okay. So I'm just trying to digest a little bit about this method of characteristics. And I guess like, so the idea is like the solutions form some surface embedded in R3 to a PDE. And we want to find the surface whose normal is, like UX, UI -1, or whatever it is based on the PDE that you have, constrained by the PDE itself. So like,
Say that again. I lost the last part.
okay, so the solutions are a surface in R3, embedded in R3, and we pick a point on that surface, like X0, Y0.
Yeah, sure. So that could be like here.
Yeah. And then what you want to do is find a curve that passes through that point while also staying on the surface.
Right. So that would be your characteristic, right? Is you
Right.
can you could define the surface just as, z equals u of xy, and that would create some, that would create some surface that cuts through R3. And then this, the function u minus z is going to be the surface. So if you take the gradient of that, it's just going to be the normal pointing down from that surface.
Right.
And then the thing that tells you how to move along that surface
Is the tangent.
is the coefficients of the PDE, because that controls, those are like your levers that controls the speed as you move along this surface, A, B, C. So then, the PDE itself is just the dot product of those two, the normal and the coefficients that move you along the surface. So that dot product could be 0 because of this orthogonality.
Right. And so I guess to sort of go ahead of what the lecture did, but what you'll probably do on Wednesday, is the idea like you have an equation, you have like, in this case, you would have like 3 equations for each component of the tangent, and those would be equal to your coefficients.
Yeah, so if you remember the total derivative, it's like now we're going to differentiate with respect to tau.
Right.
And so you'll get dx d tau.
Right. And
you'll get a dy d tau. You'll get a z d tau, right? And then, the way everything sort of spills out when you do this total derivative is that you'll use chain rule, right? I'm going to differentiate u with respect to tau. And then I'm going to look in my first argument. What's in my first argument? Oh, it's x. But x itself is a function of tau. So I get a u sub x multiplied by dx d tau, right? I'm going to get a u sub y multiplied by dy d tau, right? And then I'm just going to get a the du d tau term is going to correspond to my c, the right hand side in that case, right? So then that's like my total derivative with respect to tau.
Right.
So that's a little bit hidden in the transport equation because t corresponds directly to tau, but that's where we're going with this. Yeah.
Okay.
Yeah. So the idea is you want to create ODEs where when you take the total derivative, du d tau and dy d tau correspond to those coefficients that I just circled there.
So then the only thing that's left is like, what would like x0 comma s be? or like the initial conditions for those ODEs.
Yeah, so that's going to be that's going to be this x0s, right? And this y0s, right? So in our case, like, you know, for a time-dependent initial boundary value problem, t is just 0 on the initial condition, right? If you just have a flat initial condition, maybe you don't have an initial boundary value problem. I mean, you just have, all you have is an initial condition. T is just 0 on that. So in that case, your y0 would, you know, it'd be like your t0 would be equal to 0. And then x0 would be x, right? Because your parameterized curve would be this. If you want something more complicated, right, you could imagine, you know, you have your xy plane, and this is your initial curve here, right? And I don't know, you know, this could be the curve y equals 1 over x, right? So then your initial curve would be like 1 over x minus y equals 0. And so these would be the, you know, x0 and y0 in that case. You may also have, you know, boundary data that's like this. You know, you may have straight lines along each here, in which case typically what you do is you cut this in half, sort of like we did for the linear transport equation. And we say, you know, this is one part of our parameterized surface. I'm going to apply method of characteristics to that. You know, this is the line where I just have, you know, x and then y equals 0. And then this is the line where I have x equals 0 and y, right? So in this case, this is your x0, and this is your y0, and this is your x0, and this is your y0, right?
Thanks.
We usually don't even do anything this complicated. You're usually either doing this or you just have some, you know, x is r kind of initial condition, and then t equals 0 in this case, right? And then stuff, you know, these are your characteristics emanating, you know, from that somehow, right? So this would be your x of s tau, right? So each movement through this is a different value of tau, right? So this could be tau equals 1, this could be tau equals 2, this could be tau equals 3. So tau is, you know, sometimes going to be a warped version of t or y, and sometimes it's just going to correspond directly to t. And then, you know, these are different values of s. This could be like, you know, s equals -2, s equals -1, s equals 0, s equals 1. Yeah, so that's where we're going.
All right, thanks.
Yeah, no problem. And so I'll kind of recap that next time. Yep. See ya.
So on the signaling problem for the homework,
Yes.
look like they're out of the domain to me. So I'm not sure how to work with that. Like, based on their definition, can BT can you have like a BT and T, or wouldn't that mean X is greater than BT?
So, well, BT is defining your domain, right?
Right.
So your domain for this problem is it's not just like x is greater than 0. It's like this is your domain, right? It's going to be BT.
Right.
This is the line x equals BT. And then this is the line t equals 0, right? Because this is your x-axis here, right? And then this would be like your t-axis here, right? So this is like your, you can call this your capital omega or something like that, or your capital D. That's your domain. And then your
Our initial values are on the borders. I didn't think this.
Sorry, say that again.
Our initial conditions are defined on the like borders of this guy at like when t equals 0 and
Yeah, so along this, you have f of t, right?
right.
Defined along here, and then your initial condition here is going to be g of x, right? And so it's just going to be like a linear transport equation, right? You're going to propagate this, right? But then there's a dividing line here where x equals t, right? And so over here is where so in this region over here, that's where solutions are defined by the boundary data.
I guess I'm still confused as like how could g of x be defined because t is not allowed to be 0.
So your boundary and initial data are going to be functions that are defined on regions where the PD is not defined.
Oh, okay.
So the PD is defined away from the boundaries, and then the boundaries give you what your function u should be there.
Okay.
And then if to fit, to fill everything in the middle, you say, how do I propagate, the boundary and the initial data into that domain on the inside?
Okay. That makes sense.
Yeah. Yeah, sorry, it was probably what you were asking up front, but it took me a while to get to it.
Perfect. Thank you. That's all I had.
Yeah, no problem, Kyle. Yeah. You have a question, Serena?
Yeah.